Hello, everybody. My name is Concha Monje from University Carlos III of Madrid in Spain. And I am a member of the Robotics Lab in this university. And together with my colleagues, you can see the names there in the slide. I am happy to be here in Humanoids 2020 in this workshop on floating-based robots in manufacturing and logistics operations. And I am going to present the work with title Fractional Order Control of Soft Robotic Links. The outline of the presentation is as follows: objectives, the platform itself, the link itself, the modeling of the system, the control strategy, experimental results and conclusions, and future works, right? So the objectives of this work are the following ones. First of all, we want to design a soft link. A soft link to be used as a part of any type of robots, maybe a mobile robot, a floating-based robot, a humanoid robot, any type of robots that, in which you can integrate this soft link for different purposes. We have used this link as a soft neck for the humanoid robot tail, but also as a soft arm, right? So there are different functionalities. And of course, the design should be prepared to support all type of functionalities. Even we can connect different links to each other and have a multi-modular soft robot itself, right? Which is one of the purpose of our future work. So the idea is, is to design the system, to model the system, and then to control the system using a particular type of controllers, which are called fractional order controllers, because they can guarantee robustness of the system in the terms we will see later, right? The system we are proposing, the link, the soft link, is very, very simplified when it comes to modeling. We totally agree with that. There is a strong simplification of the model, but it is later the controller, the one responsible for facing the mismatches, the non-linearities that we have neglected, and so on. So a robust strategy from the control point of view will be developed, and we will demonstrate that even if the model is not that accurate and complete, we can manage to control very robustly the whole system, right? So if we concentrate on the platform, it has evolved during the time, but this is the base of it, right? So we have, as you can see, a fixed base, and then a mobile platform. Well, these sticks here are to allocate different masses, because we want the system to be robust to different masses on the tip, on the top of the system, right? So this is tendon actuated, right? So we have 3 motors here connected to a winch, each of them, and then the winch connected to a tendon or a cable. So moving or acting on the motor's angular position, what we do is to vary the length of the different tendons, and according to that variation, we are moving the platform, right? So this is quite simple to understand, right? And of course, this is a 3 degrees of freedom soft continuum link that you can see here, the blue one. It is modeled as an elastic beam undergoing large deformations, and also, of course, we can interchange the link, replacing it by different type of links, like, for instance, steel, spring, or a ninja flex neck, which is the final link we are using. Of course, the model uncertainties are mainly characterized by the nonlinear material, the variable mass that we can have on the tip, and also the gravity effects, as we will see later, right? So if we present the configuration here, the main mechanism configuration in this figure number 3, we can see that acting on the tendons, changing the length of the tendons, I can achieve 2 different angles here. The complete pose is composed by 2 main angles, which are the inclination angle and the orientation angle. So as you can see here, this theta s angle is the orientation that can vary from 0 to 360. So I can orientate the soft link in the whole lap, right? And also I have this inclination angle theta p, right? Okay, then let's continue with the model itself, because what we have to do here is to obtain the inverse kinematics. So why the inverse kinematics? Because if for a particular pose, right, theta s and theta p, I obtained the length of the cables, right, then it means that I can later relate that length of the cables with the particular angular position of each motor acting on the tendons. And then I can say, okay, I can control each motor to achieve each particular angular position of them, right? Then I would be controlling the whole system to achieve that particular pose. So the inverse kinematics problem is as follows. For a particular theta p and theta s set of angles, right, which is the pose, I determine the different lengths. And then I relate each length with a particular angular position of the motor. So finally, the control problem, in a very summarized way, is reduced to just simply controlling the motor position that we have, right, at each motor level, and then controlling that, I will achieve the particular pose. And so the transfer function of each motor in a first approach is, as usual, a second order transfer function if we relate the velocity input and the velocity output, right? So finally, controlling this transfer function, which is modeling each motor, so that I can achieve particular angular positions, which is the same as saying particular lengths of my tendons, I would be able to achieve particular poses. And this is the problem, right? Okay, so of course, under this assumption, we are assuming a lot of simplifications. First of all, the stiffness properties of the beam are considered isotropic and linear elastic. The tendons are also inelastic. No dynamic effects on the beam are considered. Only the actuator dynamics remains. This is important. In order to linearize the system dynamics, we assume that the beam deforms with a constant curvature. We will see that later physically on the videos. So finally, what we have is that the system has these two angles, theta s and theta p, which are the ones defining the pose only, right? And then the stiffness in shear and axial deformation directions is infinity. Only the bending stiffness remains. These are the assumptions. I agree, these are strong assumptions, but let's see later how the controller behaves to face the reality when really controlling the real platform. That includes, of course, all non-linearities, mismatches, etc. We will see how the controller is able to face this, right? So let's concentrate on the modeling, taking these assumptions into account, and let's face two different perspectives, right? The first case is an encoder-based control. So what we do here is based on the following assumptions and the inverse kinematics I presented previously. The thing is that, okay, I have a motor, 3 motors that I have to control in angular position, and I know that this is the transfer function characterizing each dynamics of the motor, right? So I can characterize that transfer function, and these are the parameters k, omega, n, and delta, typical parameters in a second order system, right? So, but since I am interested in measuring the angular position of the velocity, then I can integrate there the encoder model so that I can measure the position, which is, as you know, given by a transfer function, which is an integrator. So I cascade this transfer function GS with an integrator 1 over S. And this is the whole final transfer function, the whole model. Here you have a bow diagram. And of course, you can see that the complete model is there in frequency. So later, this would be the frequency behavior I will use as a reference to design the controller, right? So I repeat, with this transfer function, controlling these dynamics, I am neglecting everything coming next, the nonlinearity of the link, everything, right? Then controlling this, I will try and control the pose of the system. We will see, of course, the errors we are committing and that this approach is not the best possible. But let's see how we can even, if it is not the best, we can even control the system quite accurately, right? Okay, the other option is, okay, this is an encoder-based strategy, but of course we are neglecting the dynamics of the link. Why not to include that dynamics in the identification? Of course, this is what we do, and we use for that the inertial measurement unit that the system has, right, on the tip. So what we do for this identification is very simple. As an input to the system, I use a step, an inclination step signal, right? So that for that inclination commanded, I measure the final inclination of the tip using the IMU sensor, right? So if I relate this output inclination and with the input inclination, I can characterize the system with a simple first order transfer function, as you can see here with K and T, these two ones in the slide. So I can also represent the bow diagram and also the temporal response, the time and the step response of the system. So this can be the model to control. And in here we are introducing, in a linearized way, of course, the model of the link itself. Okay, then let's design controllers for each of the cases, and let's see the differences, right? So the controller strategy itself. So what is the problem when using this type of links? Of course, we have model uncertainties, as you can see here. Which type of uncertainties? This is important because not all uncertainties are considered, of course. But there is something logical here. If I am using this as an elastic link, it should be prepared to support different loads, different masses at the top. So imagine this is a neck. So the head of the robot can vary in mass, right? And the controller, the system itself, should be able to manage that mass variation. And then I have to see and characterize how the different masses on the top how they affect the final model. And also, we have to take into account that we are building this with a rapid prototyping strategy. So we are using 3D printers, and very, very rapidly we build the link and we ensemble everything, right? So, of course, there are different elements or different elements guaranteeing or not just guaranteeing, but different elements affecting the final model. For instance, if you have the pulleys and you change a little bit the position of the pulleys that we have, right? Of course, this is affecting the final model. But we want the controller to be robust enough so that if I slightly change the pulleys in the final prototype, we don't have to retune the controller over and over and over again. This is the thing, right? So we have studied that mainly mass variation affects directly the gain of the system. So when changing the mass, of course, the mass is changing different parameters in the model, but the main affected one is the gain of the transfer functions we have designed. So we need something which is a controller which is robust to gain variations. Let's see. So the controller specifications, taking all these into account, are to be selected very carefully. So we have selected 3 main controller specifications. First of all, we have the phase margin and gain crossover frequency specifications. Why in the frequency domain? Because our controllers are tuned in the frequency domain, right? So what can we guarantee, including these two control specifications as phase margin and gain crossover frequency? With the phase margin, what I determine or I force is a particular damping of the system, right? The overshoot of the system is totally directly related to the phase margin. And with the gain crossover frequency, I am controlling the speed of the system. The higher the gain crossover frequency, the faster the system. So adjusting these two, I am modulating the transient response, right? I want the system to be fast or maybe slow, and of course I want the system to have a particular overshoot. The bigger the phase margin, the lower the overshoot. But of course, I also want the system to be robust to mass variation. Then it means that I want it to be robust to gain variations. So what is that constraint guaranteeing that, as we said before? Well, we have demonstrated in previous works that there is a main control constraint that guarantees that you achieve robustness to gain variation, which is this third control constraint that tells you that variations in the bow diagram, right? Variations of the phase of the open loop system around the frequency of interest, which is the crossover frequency, are zero. So why? Because if we guarantee that we have a flat phase around that frequency, it means that if we change the gain in the magnitude curve, I can see differences, but when checking the phase margin, there is no variation of the phase margin. So whatever the mass I place on the tip, of course the system can be faster or slower, but the overshoot will keep constant, as we will see in the following slides. So these are the main points to be considered here. We will see now the results. So if we tune a controller first of all, for the encoder-based case, right, with that transfer function of second order plus the integrator, which is giving us the behavior of the encoder, this is the resulting controller, right? So first of all, I have three control constraints or restrictions, which are the phase margin, the gain crossover frequency, and the robustness to variation in the gain of the plant. And look at the structure of this controller. This is a PD controller, as you can see, but instead of using integral order controller, I am using fractional order controller. So if you look at the order of the derivative of the PD, the derivative action, instead of being one integer, I am using a fractional order, right? So this is fractional order control. Here you can see two main papers introducing these and showing all the properties of that and very good results when applying to soft robotics, right? So in fact, what we do here is to tune these three parameters: KP, proportional gain, KD, derivative gain, but also the order of the derivative. And then I have three parameters to tune, but I also have three specifications, three equations, right? So I can tune the controller using a lot of different types of tuning methods. Of course, one of them is to solve this set of three nonlinear equations with three parameters. You can use optimization for that. But our purpose here is to tune, to select these three parameters in a graphical way, very intuitively, and with graphically relating the three constants here with these three specifications. So I really encourage you to read these two papers here, references 1 and 2, so that you can really see how it is achieved, right? So of course, this extension of the typical PD controller to this fractional order PD controller is an advantage. So look at the resulting control effect in the frequency. Of course, you can see here that around 1 radian per second, which is the gain crossover frequency, the phase is flat. So if I go to the gain or to the magnitude curve, imagine that you increase it or decrease it. You would be changing the gain crossover frequency, but when you go down and check the phase margin keeps the same. So this is translated into this effect. In time domain, the overshoot keeps constant. Of course, different gains affect the speed of the system. This is faster, this is slower, but the overshoot keeps the same. This is robustness for us. And again, if we apply the same, but now tuning the controller for the other transfer function corresponding to the IMU-based system, you can here, what we tune is a PI, not a PD, but a PI, okay? This is just to show you that you can tune any type of controller, PI, PD, PID, and this is negative, so it means this is an integrator, that's why this is a PI. And again, you can see here how the phase is flat, and then variations of the gain are just translated into faster or slower responses, but with SIBO overshoot variation, right? So let's see the experimental results. Of course, we have implemented the whole scheme physically, right? So the idea is that I command the inclination and orientation of the platform. I calculate the inverse kinematics. And then from the inverse kinematics, I reach the values of the lengths of the tendons, L1, L2, and L3. And this is translated into a particular angular position target for the 3 motors. And then the motors are controlled with the PID, fractional, integer, whatever, for the sake of comparison. And then I can measure the results. So look at the case in which we have the encoder-based control. What we do, here you can see the neck. First of all, the load is SIBO mass at the tip. So we are commanding different inclinations from 0 to 15 at all possible orientations, right? So we are orienting the neck in the whole round, and for each orientation, we are achieving inclinations of 15 degrees. This is what we do. The mass of the neck is 16 grains, and the face mass is 125 grains. So you can see here that the system is under control, of course, just based on the encoder measurement. So we are from the encoder measurements, we are closing the loop. Here you can see what happens when we load the system with 100 grains. So it's totally under control, and I would like to go directly to the case of 500 grains. So you can see that the system is robust. There is no problem, even if the mass is very, very high and the neck mass is very small, 16 grains, the system performs correctly. But look at the results. Of course, if we trust just on the kinematics that we have calculated before, we can see that the positions, the poses are achieved almost without any error, just neglectable errors. But look at the real measurement. This is telling us that the IMU system is telling us that the inclination and the orientations are not exactly the ones demanded or commanded. We can see that especially for the worst case, which is the higher mass, 500 grains, right? There is a difference. So apparently the encoders are telling me that I am achieving that pose, but the reality is that the IMU sensor is telling me, no, you are not achieving it. And there are differences if you select one mass or the other. Right? The same applies for the orientation, even if the orientation is better. By the way, these jumps that you can see here are just simply because around SIBO, it is difficult to determine if the orientation is SIBO or 360 degrees, right? In future works, we have in following works, we have solved this problem. So let's see now with the IMU. Well, for sure, the control signals are totally under control, and there is no saturation, and we can control this with simple control signals, right? So let's see now what happens if I use the IMU feedback. I apply the same. Here you can see again the neck. Let's see that for the maximum mass, which is 500 grams, of course the system is robust. Here you can see all the masses placed on the tip. And if we analyze the results now, of course, since we are using that information to close the loop, we are controlling more accurately. And the important thing is that you can see that for whatever the mass, the system keeps robust. This is important, right? And this is the type of robustness we are looking for. Here you can see again the control laws, which are simple, soft, and totally feasible for the system, right? So if we integrate the neck on tail, we can see that we, of course, can have these different movements and versatile movements for the robot's neck. So you can see here that of course the system is just simply following some references paths, and we can control this with a 3D mouse or just commanding fixed trajectories. You can see that sometimes the neck moves a little bit, and this is because it is not very well attached to the trunk of the robot, not because this is shaking or showing vibrations, right? So this is one of the things we have achieved, but we have, of course, evolved. Why? Because we try to use that link not as a neck, but as an arm, right? This is more interesting from our perspective. So the thing is that the structure wasn't able to support bending masses. If you want to manipulate a mass in the horizontal position as an arm, grasping loads and placing them here and there, then you would need a more robust structure. And also we wanted to integrate the tendons inside the structure and so on. So we achieved this design. You can see here that you can print using 3D printers with Ninja Flex material, or why not a 2-component silicon from a mold, right? So, but this is the final design. So if you look at the workbench we have a set, you can see that again you have 3 tendons, 3 motors placed as in this graph, and this is the solution that we have achieved. So in here you can see how the range of movements is higher, more controlled, and the curvature, because of since we have integrated the tendons inside the structure, now the constant curvature assumption is better achieved, right? So modeling is more accurate, and also the control is more effective. So we are now testing this platform with the different loads, and this is working perfectly well. In future works, you will be able to see that. We are finishing these experiments right now, right? So this is one of the main achievements, and I would like to share with you another type of design in which we have replaced the tendons by shape memory alloy actuation. So now the tendons are not inelastic, but they are actuators itself by themselves, right? So what we do with this shape memory alloy material is when we heat it, when we heat the material, the length changes, and then controlling with currents the different tendons, I can vary the length, and then I can control the system. So this step implies that we are also considering not just a flexible link or a soft link, but also a soft actuation, right? And this is important. Of course, there are a lot of work to be done from this side, but we are confident that we can achieve very good results integrating SMA actuation into the system. And just to finish, I would like to conclude showing or summarizing the main objectives we have achieved. For sure, we have modeled, we have implemented, designed, first of all, built also, and then modeled and controlled the soft link, different soft links that I have presented here to you. And finally, the control strategy we have used is the fractional order control strategy, because it guarantees robustness to mass variation, mainly in these type of systems, but also other mismatches and in the system modeling, right? I really encourage you to read all the references. They are open access so that you can have more information about the type of controllers I am presenting you. And of course, this robustness that I introduced in the system is able to face all the mismatches of the simplifications of the model we are assuming, right? In future works, of course, we have to improve a lot the designs we have developed so far, but we are also integrating a new type of link, which is an origami-based soft link, as you can see here. So we have designed these based on an origami structure, and with the motor, we can control the orientation of the, and also the length of the structure of the origami, right? So this is our first approach we have published in this mathematics paper, as you can see here, reference number 5. We are quite happy that this paper has been very well considered. This is now the in the front of the journal and as opening the journal issue. So we are quite happy. And of course, still there are many things to do here, but this is an approach we would like to keep working on in the future. So this is my presentation. I hope you have liked the different modeling and control objectives I have presented, and I will be very happy to solve any doubts, any questions you may have. Of course, see you in Humanoids 2020 live session. And of course, you can also contact me by email. I will be very happy to share my ideas with you. Thank you very much.